Let's dive into how you can take a machine learning project from start to finish. We'll walk through the typical steps and I'll show you how these apply when you're dealing with, say, genomics or clinical information using a solid example, predicting breast tumor malignancy. First things first, you've got to understand the overall aim. Pretend we're data scientists at a biotech company and our mission is to predict whether a breast tumor is malignant, that's cancerous, or benign, non-cancerous, based on measurements from cell nuclei. This is a classical bioinformatics problem and it's super relevant. The data we'll be using is the Wisconsin breast cancer dataset. It's a readily available public dataset, and while it's not the absolute newest, it's fantastic for learning the ropes of the whole machine learning process. So the main steps we'll cover are as follows. We'll start by looking at the big picture, what we're actually trying to achieve here. Then we'll get our hands on the data. Where does it come from and how do we load it? Then we'll explore and visualize the data to spot patterns and gain some initial insights. This is like our first conversation with the data. Then we'll prepare our data so our machine learning algorithms can actually use it effectively. This is a big one in bioinformatics. Then we'll select a model and train it. We'll go over fine-tuning that model to make it even better. We'll figure out how to present our solution and what we've found. And finally, we'll think about how to launch, monitor, and maintain our system if it were a real tool going live. When you're learning, it's better to use real-world datasets, not just made-up ones. Real data has all the quirks and challenges you'll face in real projects. For bioinformatics, there are tons of places to find data. Think NCBI, particularly their GEO database, the Cancer Genome Atlas, TCGA. You have ArrayExpress, the Human Protein Atlas, or even general spots like Kaggle that often have bioinformatics challenges. For our example, we'll use the Wisconsin breast cancer dataset, which is conveniently packaged right into Scikit-Learn, making it super easy to get started. So for our breast cancer prediction task, what's the actual objective? It's not just about building a model. We want to build a model that can accurately classify tumors to help doctors make better, more informed decisions. This prediction could, for example, feed into a larger clinical decision support system, acting as a helpful tool for pathologists. Think about how it's currently done. Pathologists look at cell morphology, so their shape, size, structure, and arrangement. This is a detailed and skilled process. A robust machine learning model could provide a quantitative, reproducible second opinion, or even help identify subtle patterns that are hard for the human eye to catch consistently. Now let's break down what kind of machine learning problem this is. If you remember from the previous video, we can categorize machine learning systems in a few ways, by supervision, learning style, and generalization. For our breast cancer use case, it's a supervised task because we have labeled data. Each tumor sample comes with a known diagnosis, either malignant or benign. The model learns from these known outcomes. And since the outcome is a category, either malignant or benign, it's a classification task. More specifically, it's a binary classification because there are only two classes. Remember, there are many different models that can be used for a supervised classification task. For example, you have regression models like logistic regression, you have decision trees and random forests, support vector machines, among others. But I don't expect you to know about all of these for now. We'll cover these later in the series. And later in this video, we'll get into picking and testing some models. All we're doing here is defining that this is a classification task. We can also think about the learning style. Here we're likely using batch learning, meaning we'll train the model on all available historical data at once. This is pretty common when you have a dataset ready to go and you're not expecting a continuous stream of new data that requires the model to update instantly. And finally, let's talk about generalization. This is how our model performs on new, unseen data. We're aiming for a model-based approach here. What does that mean? Well, we'll start by selecting a model type, like logistic regression or random forest, which learns patterns from labeled data to distinguish malignant from benign tumors. The goal is for the model to generalize these patterns, making accurate predictions on unseen samples, hence why we use a test set to evaluate its ability beyond memorization. Unlike instance-based learning, where methods like k-nearest neighbors rely on direct comparisons to stored examples, a model-based approach builds a predictive model that captures the broader underlying patterns in the data. So to recap, we have a supervised classification, batch learning, and aiming for good generalization with a model-based approach. That frames our problem nicely. Okay, the next question we want to think about is, how do we know if our model is any good? We need a way to measure its performance. The type of metric we choose depends heavily on the kind of problem we're solving, whether it's classification, regression, or something else. For our breast cancer problem, which is a classification task, here are some common and important metrics that we'll consider. So first, accuracy. This is the most straightforward one. It's simply the proportion of predictions our model got right. So if it correctly diagnosed 95 out of 100 tumors, the accuracy is 95%. While easy to understand, accuracy can sometimes be misleading, especially if one class is much more common than the other. This is called class imbalance. For example, if 99% of tumors in a dataset were benign, a model that always predicts benign would have a 99% accuracy rate, but it would be useless for detecting cancer. Then we have precision. This answers the question, of all the tumours our model predicted as malignant, what proportion actually were malignant? High precision is important when the cost of a false positive is high. A false positive means a benign tumour is flagged as potentially cancerous, leading to further tests and patient anxiety. We want to minimise these. Next we have recall, also called sensitivity or true positive rate. This answers, of all the tumours that truly were malignant, what proportion did our model correctly identify? High recall is absolutely critical in medical diagnosis like ours. A false negative, so missing an actual malignant tumour and calling it benign, can have severe consequences. We want to catch as many malignant cases as possible. Then we have F1 score. Often there's a trade-off between precision and recall. If you make your model very cautious about calling anything malignant to improve precision, you might miss some actual malignant cases, which lowers recall. The F1 score is a handy way to combine precision and recall into a single metric. It's the harmonic mean of the two, so it gives more weight to lower values. A high F1 score means both your precision and recall are reasonably good. It's useful when you care about both minimizing false positives and minimizing false negatives. And then finally here we have area under the ROC curve, or AUC-ROC. This one sounds a bit more complex, but it's a very powerful and widely used metric for binary classification. Now let's break this one down a bit more. So many classification models don't just output malignant or benign. They often output a probability or a score indicating how confident they are. For example, 0.9 probability of being malignant. We then need to pick a threshold for this probability. If the probability is above the threshold, we call it malignant, otherwise benign. The ROC curve plots the true positive rate, also known as the recall, against the false positive rate. And it does this for all possible threshold values. If the area under this curve is 1, which would essentially be like this, it's a perfect classifier, meaning it can perfectly separate the two classes. An area under this curve of 0.5 means the model is no better than random guessing, like flipping a coin. The closer the area under the curve is to 1, the better the model is at discriminating between the classes. It's particularly good when your classes are imbalanced because it considers performance across all decision points. For our cancer diagnosis problem, minimizing false negatives, so failing to detect a malignant tumor, is often paramount, making recall for the malignant class very important. However, the AUC-ROC gives an excellent overall measure of the model's discriminative power across different trade-offs. So we'll probably aim to maximize the area under the ROC curve while also keeping a very close eye on recall for the malignant class and perhaps the F1 score to ensure a good balance. Again, this might be a little overwhelming at first, but all we're doing here is deciding on how we'll measure our model's performance. The ways shown here are tried and tested methods, and the ones we choose to focus on will depend on the problem at hand. Okay, one final thing before we dig into the code. It's always good practice to list out your assumptions early on. Here's ours for this problem. We're assuming that the features measured from the cell nuclei, like cell radius, texture, and concavity, are indeed relevant for predicting malignancy. Now, I know you haven't actually seen the data yet, but if we just take a quick sneak peek, you'll be able to see some of the measurements in our dataset. So we have radius, texture, perimeter, area, smoothness, etc. over many different cancer cells. Okay, the second assumption we're making is that our dataset is a fair representation of the types of tumors we want our model to work with in the future. We also assume the labels, malignant and benign, in our dataset are accurate. This is going to be our ground truth. And then finally, we assume that whatever system uses our model's output, like that clinician decision tool, can take what our model gives it, maybe a probability score of being malignant. Okay, let's go over to the code now. A quick note before we dive in, I'll link to the full Jupyter notebook for this tutorial in the video description, and I highly encourage you to open it up and code along, or at least follow along with the notebook. I've already written and tested all the code, so it's ready to go, and please feel free to pause the video, tinker with the code, change parameters, and explore if there's anything that sparks your curiosity or isn't immediately clear. That's often the best way to learn. First up, we need to import all the libraries that we'll be using. So we'll be using Python with our standard toolkit, NumPy for numerical computing, Pandas for handling data in tables, Matplotlib and Seaborn for plotting, and of course Scikit-Learn for all the machine learning magic. So within Scikit-Learn, there's a module called Datasets. This datasets module contains a variety of toy datasets that are really useful for learning and demonstrating algorithms, as well as functions to load or generate more complex datasets. From this Scikit-Learn datasets module, we're going to specifically import one of these pre-packaged datasets, load breast cancer. Then we actually load the dataset by calling the load breast cancer function that we just imported. This function, when called, does all the work of fetching the dataset's information, so the target labels, feature names, etc., and bundles it all up. We'll store the result of this function in a variable called cancer. So what is this cancer variable now? Well, it's a Scikit-Learn bunch object. You can think of a bunch object as being similar to a Python dictionary, but you can also access its content using dot notation. So in a normal Python dictionary, you'd access information using notation like this. However, with the Scikit-Learn bunch objects, you can also use dot notation. So for example, like this. It's just a convenient way Scikit-Learn packages datasets. Now, this cancer object itself is worth exploring if you're new to Scikit-Learn datasets. This is a great point where I encourage you to pause and tinker. For example, you could add some lines of code in your own notebook looking at the attributes inside this object. To see all the different attributes this cancer object holds, you can use the dir function. So print dir cancer like this. And if we run this, you can see we have the following. So this is a string containing a full description of the dataset. Data is a NumPy array holding all the feature values for each sample. We also have a bunch of other stuff. For example, feature names is a list of strings with the names of each feature column, and target names is a list of strings with the names of the target classes, e.g. malignant or benign. So let's actually take a look at a couple of these attributes using the dot notation. So we're going to look at the description string and the NumPy array that holds the feature values for each sample. So if we run this, and I'll just get rid of this red text, and if we scroll down now, you can see the following. So again, we have the attributes of the object, and then we have this description string telling us all about the data set. And then also at the end here, we have the NumPy array, which is the data attribute of that bunch object. And again, this is just an array holding all the feature values for each sample. So while this bunch object is useful for most data manipulation and exploration tasks, a pandas data frame is much more convenient. So our next step is to convert this data into a data frame. And FYI, from now on, I won't be typing any code on the fly. I'll just be running the pre-written code in the notebook. But to reiterate what I said earlier, I encourage you to go in and explore and tinker with things, as this is often the best way to learn. Okay, so in this next cell, we create our data frame, which we call df, using the pandas data frame function. We tell pandas the data should come from the data attribute, which is the NumPy array of feature values, and that the names for the columns should come from cancer.featurenames. And printing the head of this data frame, you can see now all the measurements we have in our dataset. So there are 30 different columns in our dataset. It's just been reduced so that it fits on the screen. Okay, next we need our target variable, the diagnosis, as a new column in this data frame. The actual diagnoses are stored in cancer.target. Now, an important detail about this specific Scikit-Learn dataset, cancer.target often labels malignant tumors as 0 and benign ones as 1. For our analysis, and because it's a common convention in many machine learning contexts to have the positive class, so the one we're trying to detect, like malignant represented by 1, we're going to flip this around. So we create a diagnosis column where malignant tumors will now be 1 in our diagnosis column and benign tumors will be 0. So if I just run this cell, we print a success message, and the shape of our data frame, that's the number of rows and columns, just to confirm it's loaded correctly and has the dimensions that we expect. And then just to be absolutely sure about our target mapping, we print the unique values from the original cancer.target, which is a NumPy array, and then the unique values and accounts from our new df diagnosis column, which is a pandas series. This confirms that our diagnosis column now correctly has 1 for malignant cases and 0 for benign cases. And we can see how many of each we have in the dataset. With our data frame df ready, the next few cells in the notebook are for taking a quick initial look at its structure. So running this cell will show us several outputs. df head shows us the first 5 rows, giving a snapshot of the data and all the feature columns. So we should see our new column at the end here, which is the diagnosis column, which we just added. df info is super useful. It tells us we have 569 entries, 31 columns, lists each column the number of non-null values, which we can see there are no missing values here, which is great. And also the data types, mostly float64 for features and then int64 for our diagnosis. And then also we use df describe, and this gives us some statistical summary. So for each numerical column, you see the count, mean, standard deviation, min, max, and the quartiles as well. Okay, so next up in the notebook is plotting some histograms to visualize the distributions of features between benign and malignant tumors. I'll go ahead and run it, and then we can talk through the code. Okay, so here's the output. So essentially for each feature, we're looking at the distribution of samples between malignant and benign. So just to quickly touch on the code, this part here selects all the feature column names, and then we essentially use Seaborn and matplotlib to plot histograms for each feature, showing malignant samples in red or the salmon color, and then benign samples in this sky blue color. If we look at the output histograms, you really start to get a feel for each feature. For example, you might notice for features like mean radius that the salmon distribution, which is the malignant, is clearly shifted towards higher values compared to this sky blue distribution, which is our benign samples. And this visual separation is exactly what we're looking for. It suggests these features are likely good predictors for distinguishing between malignant and benign tumors. Now, other features might show less separation, like the mean symmetry over here, here. These overlap quite a lot. So this initial visual exploratory data analysis is invaluable for seeing what features we might want to include in our predictive model. And I'll just scroll to the bottom so we can see all of them here. There's another good one, worst radius. These are quite good as well. And worst concave points, that's very good in terms of distinguishing between malignant and benign. So yeah, definitely a lot of great options there for our model. Now, before we go any further with exploration or start building any models, we hit a critical step, and that is creating our training and test sets, as you see in this cell of our notebook. So let's talk through what this code does. First, we make sure we have train test split imported from Scikit-Learn model selection. This is Scikit-Learn's go-to function for splitting datasets. This line then creates our feature matrix, which we're calling X, capital X. It takes our main data frame, DF, and drops the diagnosis column. Next, this line creates our target vector, Y, which is just the diagnosis column containing our zeros and ones. And the most important line here is this one. This train test split function takes our full X and Y as input, as well as specifying that we want 20% of the data to be set aside for the test set, so the remaining 80% will form our training set. And we also give another couple of parameters. So random state 42 is a convention to ensure that if we run the script again, we'll get exactly the same split. This is crucial for reproducibility. So you can use any integer here. And then this final parameter, stratify equal to Y. This is important for classification tasks. It essentially ensures that the proportion of malignant and benign tumors in our original Y is maintained in both the Y train and Y test sets. This prevents one set from accidentally getting, say, almost all malignant samples. And then the print statements at the end of this block will show us the shapes of our new sets and, crucially, the distribution of classes in Y train and Y test. So as you can see in the output, the percentage of benign and malignant tumors is very similar in the training set and the test set here. So we've got 0.626, 0.31, 0.37, 0.368. This confirms our stratification worked perfectly. Now, from this moment forward, X test and Y test are metaphorically locked away. We'll not touch them or look at them until the very end of our project, when we want to evaluate our final best model. All further exploration, processing, and model training will happen only on X train and Y train. With our test set safely tucked away, let's dive deeper into exploring our X train and Y train. One powerful way to get an overview of high dimensional data is using dimensionality reduction techniques for visualization, like UMAP. So in this next cell, we'll apply UMAP to our training data. So first we import standard scalar from Scikit-Learn preprocessing and UMAP from the UMAP library. If you're running this locally, you might have to install these first with pip install library. So UMAP generally works best on scaled data. So this line here scales our training features. Then we initialize UMAP and we specify a bunch of parameters here to control the balance between preserving local versus global structure. So n components is equal to 2 means we want to reduce the data to 2 dimensions for plotting. Random state again ensures reproducibility, and n jobs equal to 1 does also help with exact reproducibility in some environments. This line then applies our UMAP to get our 2D representation, and finally we create a scatter plot using matplotlib pyplot where we plot the first UMAP component against the second. And crucially, we color these points based on Y train, where Y train is equal to 0 are the benign samples in sky blue, and where Y train is equal to 1 is our malignant samples in this salmon color. Now, looking at this UMAP plot, we're hoping to see some visual separation between the benign and malignant samples. If the two clusters are heavily intermingled, it suggests the classification task might be more challenging. If they form somewhat distinct groups, that's a good sign. So in our case, we do see them forming these two distinct groups, so that's good. Next, let's investigate how our features correlate with each other, and more importantly, with the diagnosis. For this, we'll temporarily add the Y train, so the diagnosis column, back to a copy of X train, and we'll call this X train with target. Then we can easily calculate the full correlation matrix. This line here calculates the pairwise Pearson correlation between all columns. Then using Seaborn heat map, we visualize the correlations specifically with the diagnosis column. So if we run this, we can see what features are highly correlated with the diagnosis. So as the output shows, and as expected, diagnosis has a perfect correlation with diagnosis. But then we see these features below that have high correlation with diagnosis. So for example, worst concave points, worst perimeter, worst radius, and mean concave points. This means that as these feature values increase, the likelihood of tumor being malignant also tends to increase, which aligns with medical understanding. And we can also see the least correlated features down the bottom here. Now, there was actually also a print statement in our code block where we're essentially just printing the top 10 correlated features and the bottom 5 correlated features, which we can see here. So the top 10 and the bottom 5. Now, to get an even better visual sense of the relationships between the most promising features, we can can use a pair plot from Seaborn. So the next cell in our setup is to do exactly this. So here's what this pair plot code does. This line takes our previously sorted correlation series, gets the feature names, and then takes the top 4 features. We then print these top 4 features. So if we run this, we can see them printed as follows. So worst concave points, worst perimeter, worst radius, and mean concave points. The second half of this cell then creates a Seaborn pair plot, and this produces a matrix of plots, which we can see here. So this is showing the 4 top correlated features. We'll just zoom out slightly. So on the diagonal, you can see the distribution for each of the selected features split by diagnosis class, so malignant and benign. And in the off-diagonal scatter plots, you're looking for pairs of features where the sky blue or benign and salmon malignant dots form relatively distinct clusters to show clear separating trends. This gives a strong visual indication of which feature combinations might be particularly powerful for a classification model. So these look quite good because they're separating out into distinct clusters. Now, another excellent way to compare how feature values differ between our malignant and benign classes is by using box plots. So this next cell in our notebook here demonstrates this using the features we identified as highly correlated, plus a couple of others for variety. So if I zoom in again, this first part is just some logic to select the features that we're going to show in our box plots. Then it calculates the number of rows and columns needed for our subplot grid, and then we set up a plot using PLT figure, and the core plotting is done by the Seaborn box plot function. If any of this code is confusing, go ahead and open the notebook yourself and tinker around with it. You can also ask Gemini using the button in the top right here if anything's confusing. So when we run this cell, you'll see a series of box plots, and for each feature you'll see 2 boxes, one for benign samples and one for malignant samples. Again, benign in sky blue, malignant in salmon. So again, I'll zoom out just to get them all on the screen. What we're looking for here are features where the 2 boxes show minimal overlap and importantly have distinct different median values and overall ranges. For example, if for a feature like mean concave points, the entire salmon box plot is shifted significantly higher than the sky blue box, which is the benign samples, this strongly indicates that the mean concave points is a very useful feature for distinguishing between the 2 classes. Alright, with our initial exploration of the training data giving us some good insights, we now move on to a crucial phase, preparing the data for our machine learning algorithms. So in the notebook, the next set of cells under section 5 will focus on these preparation steps. For many real-world datasets, this stage can be the most time-consuming, but also one of the most impactful. We need to consider things like missing values, how to handle different data types like text or categories, and feature scaling. First, let's talk about missing values. Now, our Scikit-Learn breast cancer dataset is conveniently complete, so there's no missing values, which is great for a demo. But in most real-world biological or clinical datasets, you'll almost certainly encounter them. Maybe a particular lab test wasn't run for a patient or a sensor reading failed, leading to a gap in the data. So for demonstration's sake, we're going to introduce some missing values and then show how we would manage them. If we did have missing values, Scikit-Learn's simple imputer from the Scikit-Learn impute module is a very handy tool. So first, we import simple imputer. We then create a copy of xtrain and manually introduce some NAN values into the mean texture column. NAN stands for not a number, and here we print the count of NANs before imputation. So I'll go ahead and run this cell. So it says NANs before imputation 5. Next, this line creates an imputer object, and this strategy argument tells it how to fill the missing values. So common strategies are mean, median, or most frequent. The median is often a good default choice because it's robust to outliers in the data. This next line is crucial. The fit method is called only on the training data or the relevant columns of it. For the median strategy, this step calculates the median value of the mean texture column from the available data. And after fitting, this line uses the learned median to fill in or transform the NAN values in that column. So the output of this cell would show that the NANs in the mean texture column have been replaced by the calculated median. Now, since our actual xtrain is clean, we don't need to apply this for our main workflow. This is just a copy of our xtrain to demonstrate imputation. But this is a vital technique to have in your toolkit for most other datasets that you'll encounter. Okay, now let's move on to handling categorical attributes. So our breast cancer dataset contains only numerical features. However, many bioinformatics and clinical datasets include categorical information. Machine learning algorithms typically require all input to be numerical. So if we did have such categorical features, Scikit-Learn's one-hot encoder from the Scikit-Learn pre-processing module is a common solution for nominal categories where there's no inherent order between the categories. So let's look at an example cell for this. And what we're going to do here is we're going to introduce some dummy data, so some tumor grade categorical features. So we start by creating some dummy categorical data, then we initialize our one-hot encoder. We have a couple of parameters here. So sparse output equals false. This tells it to return a regular NumPy array by default it returns a sparse matrix, which is memory efficient if you have a very large number of categories and thus many new columns with mostly zeros. And then we also have a parameter handle unknown ignore. This means if the encoder encounters a new category in the data it's transforming, i.e. in the test set, that it didn't see during the fit step on the training data, it will represent that new category with all zeros in the one-hot encoded columns rather than throwing an error. This line then learns the unique categories from the tumor grade and transforms them into the one-hot encoded format. And if we just run this cell, we can see what's printed. The output shows the resulting array where each original category, so G1, G2, and G3, which are our tumor grades, has become a new binary column. You can also see the categories it found and the names of the new output features. Again, our current dataset doesn't have categorical features needing this, but one-hot encoder for nominal data and ordinal coder for data with an inherent order are key processing tools for turning your categorical features into numerical features. Now, for a step that is absolutely crucial for our current dataset, and that's feature scaling. As we observed way back in our initial data exploration, our numerical features like mean area versus mean smoothness exist on very different numerical scales. Many machine learning algorithms, particularly those that use distance calculations like k-nearest neighbors or support vector machines with certain kernels, or gradient descent like logistic regression or neural networks, they perform much better or converge faster if all input features are on a similar scale. This prevents features with larger values from inadvertently dominating the learning process. So we'll use standard scalar from Scikit-Learn pre-processing. Standard scalar will standardize the features by removing the mean and then scaling them to unit variance. This means after scaling, each feature will have a mean of approximately 0 and a standard deviation of approximately 1. And to make our workflow clean and ensure these steps are applied consistently, especially when we get to cross-validation and applying our model to the test set, we'll use Scikit-Learn's pipeline object from the Scikit-Learn pipeline module. A pipeline allows us to chain together data transformation steps and optionally a final estimator like our classifier. So let's break down what's happening in this cell. Here we define a pipeline object. This takes a list of steps. Each step is a tuple containing a name we give it, here standard scalar, and the transformer instance, here standard scalar as in the function. If we had more pre-processing for numerical features like imputation, it would be another step in this list, typically before scaling. This line calls fit transform on our pipeline with our training data. So the fit part here calculates the mean and standard deviation for each feature in XTrain, and the transform part then applies this scaling, so it subtracts the mean and then divides by the standard deviation, and this results in a numpy array containing our scaled training features. So let's run this and see what the print statements give us. So the print statements show us the shape of this scaled data and a few example values here, and as you can see, the mean of the mean radius column is now effectively 0. This is not minus 3.65, it's actually a decimal, so times 10 to the minus 15, and the standard deviation is now effectively 1. So this confirms that our standard scalar has done its job perfectly. Actually, an important point worth mentioning here is that later when we process our test data, which is in the xTest variable, or any new data for prediction, we'll only use the transform method of our already fitted NumPy pipeline. So we don't call fit transform like we did up here, we just call transform, because we must apply the exact same transformation using the means and standard deviations learned only from the xtrain data to avoid any data leakage from the test set into our model's knowledge. If we had a mix of numerical and categorical features, we'd typically use Scikit-Learn's column transformer to apply different pipelines like our num pipeline for numerical columns and a separate one-hot encoding pipeline for categorical columns to the correct subsets of columns and then combine their outputs. Since all our features in this dataset are numerical, our num pipeline applied to the entirety of xtrain is what we need. For simplicity in the next steps, when we build our full model pipelines, the standard scalar will just be the first step in those pipelines. Okay, our strategy for data preparation is clear. Now it's time to select and train some machine learning models. And since this is a binary classification task, so predicting whether a tumor is benign or malignant, we'll try a few common classification algorithms. A good practice is to start with a relatively simple model as a baseline. Logistic regression is excellent for this. It's interpretable, generally fast to train, and performs surprisingly well on many problems. We'll build a new pipeline that now includes two steps. First, our standard scalar for pre-processing the features, and second, the logistic regression model itself, which we import from Scikit-Learn's linear model module. Bundling these into a pipeline is a really robust way to ensure consistent pre-processing. So let's walk through this code. So we ensure our logistic regression is imported, as well as some evaluation metrics like accuracy score and ROC AUC score. Then we define the pipeline. So the first step is our standard scalar named scalar, and the second step is an instance of logistic regression which we've named log reg. And these parameters here, solver equals liblinear. This is often a good choice for smaller datasets and binary classification. Random state 42 is used for reproducibility reproducibility reasons. So this line here then trains the whole pipeline. It takes xtrain, passes it to the scalar step. The scalar calls fit transform on xtrain, so it learns the means and standard deviations and scaling the data. Then scaled xtrain is then passed to the log reg step, and the logistic regression model then calls fit using this scaled data and ytrain. The subsequent lines here demonstrate how to make predictions. So we'll go ahead and run this cell and we'll talk through the output. So this line here will output the predicted class labels, so 0 for benign, 1 for malignant. Now when you call predict on a pipeline, the input data automatically goes through all the transformer steps, so our scalar in this case, before hitting the final estimator's predict method. This line here then compares our predicted values versus the actual values for malignant and benign. And as we can see, we get a 0.9890 training accuracy, which is good. Then this line here gives the class probabilities. So it returns an array where each row has two values, the probability of being class 0 or benign and the probability of being class 1 malignant. And if we calculate the ROC AUC score for this prediction, we get a 0.9976 area under the curve, which is highly accurate. So this is a great start, but we need to remember that performance on the training set can be misleading due to potential overfitting. So we need cross-validation for more realistic assessment. So while our logistic regression algorithm gives us a strong baseline, let's now try a more complex model, a decision tree classifier. Decision trees can learn more intricate, non-linear patterns in the data, but they also have a higher tendency to overfit if not constrained. So the setup in the notebook for the decision tree is very similar to what we did for logistic regression using a pipeline. So first we ensure that decision tree classifier is imported from Scikit-Learn tree module. We then again define a pipeline with the first step being the standard scalar, and this time the second step being our decision tree model. This line then trains the pipeline. The data is scaled, and then the decision tree is built using the scaled data and ytrain. And finally, we evaluate its performance on the entire training set by calculating accuracy and the ROC, AUC or area under curve. So let's run this and see what we get. Wow, look at these scores. If you see an accuracy and area under curve of 1 like this, as is very common for an unconstrained decision tree on its training data, that's a massive red flag for overfitting. It means that the decision tree has learned the training examples perfectly, perhaps by growing so complex that it has a unique path for almost every sample. We'll bring up on screen now a graphic of how a decision tree algorithm works. But essentially, you're following a path of questions, and what's happening here is we're essentially getting a unique path for every sample, including any noise or specific quirks in the training data. And while it looks great on paper for the training set, it will likely not generalize well at all to new unseen data. So to get a much more reliable and realistic estimate of how our model will actually perform on unseen data, and to properly diagnose overfitting, we'll absolutely need to use k-fold cross-validation. And Scikit-Learn's cross-val score function from the Scikit-Learn model selection module is our tool to do this. So let's break down what this cell does. So we pass the entire pipeline that we want to evaluate along with our full training features and training labels. The CV equals 10 argument specifies that we want to perform 10-fold cross-validation. This means that xtrain and ytrain are split into 10 equally sized non-overlapping parts or folds. The pipeline is then trained 10 separate times in each iteration. So it takes 9 of the folds as its internal training data. The pipeline's scalar step will fit transform on these 9 folds, and then the model, e.g. logistic regression, will fit on this scale data. The pipeline is then evaluated on the one remaining holdout or validation fold. The scalar step will only transform this holdout fold using parameters learned from the 9 folds, and then the model will make predictions. This process repeats with each of the 10 folds getting a turn to be the holdout validation set. And scoring ROC tells this function that we want to use the ROC area under curve as our evaluation metric for each fold. And it returns a NumPy array containing the 10 ROC AUC scores, one from each validation fold. And we then print these scores, and more importantly their mean and validation. So let's run this. And by the way, down here we're doing the exact same thing, only this time we're using the tree pipeline instead of the logistic regression pipeline, 2 different models. So these mean values give us a more robust estimate of generalization performance, and the standard deviation tells us about the variability or stability of that performance across different subsets of our training data. If we look at the mean area under curve for the decision tree, it's significantly lower than its training area under curve, which was 1. This confirms that it was overfitting. The logistic regression's area under curve is closer to its actual training area under curve value, and it has in fact outperformed the decision tree in terms of cross-validation performance, indicating it generalizes better despite its simplicity. And the standard deviation scores are also informative. A smaller standard deviation suggests more consistent performance. So for us, the logistic regression performs better and more consistently. So I've just brought up this slide from the last video just to recap on cross-validation if you're a bit unsure. But essentially, here we have our training data set and our validation set here. What we do is we take our training set, when we're doing cross-validation, and we split it into many slices. So instead of having just a single validation set, we kind of rotate this with these different slices of the training set, and that's our cross-fold validation. So in our notebook, we were using 10-fold cross-validation, meaning we split the training set and validation set together into 10 slices, and we take one slice at a time to use as the validation set, and then we rotate that. So we essentially get 10 different combinations of training and validation data. And then also, while we're here, we can talk through kind of what else we did. So we trained our logistic regression model first, then we trained a decision tree model. We took both of those, we made predictions, and we used our area under curve and accuracy measures to get an estimate of this generalization error. And as you saw, when we didn't do cross-validation with the decision tree, it gave us a perfect prediction of 1 area under curve, but we saw that it was overfitting. So this cross-validation step is very important to make sure we're not overfitting. So let's go back to the code. Okay, what we're going to do next is try an ensemble model. So we're trying out a third model after the logistic regression and the decision tree. A random forest is essentially multiple decision trees. That's what we mean by ensemble model. We're combining multiple decision trees into one. So we're creating an ensemble. So decision trees, when used individually and unconstrained, tend to overfit. However, an ensemble of decision trees, like the random forest here, is often much more robust and typically performs well. A random forest works by training many individual decision trees, often on different random subsets of the data and features, and then it combines their prediction, e.g. by majority vote for classification or averaging for regression. This ensemble approach helps to reduce overfitting and improve generalization. So let's try that with the random forest classifier from the Scikit-Learn ensemble module. So this setup is very similar to our previous models. We first define a pipeline. This one we're calling forest pipeline. First, we again use our standard scalar, and then we use an instance of the random forest classifier, which we're calling forest CLF. And the n estimators parameter tells the model to build 100 individual decision trees in the forest. We then run 10-fold cross-validation on the forest pipeline using the cross-val score function. Again, we're scoring with ROC, AUC. So let's run this. And what we see here, when we look at the mean area under curve and the standard deviation, the model performs well. We're getting a 0.9884 for the mean area under curve with a standard deviation of 0.0185. Okay, so based on these cross-validation results, if we compared the different models we've done so far, so we get 0.9884 for random forest, and then we get 0.9953 for logistic regression and 0.9117 for decision tree, we see that logistic regression actually seems to be performing best in this scenario. However, for the sake of this tutorial, let's assume that the random forest model looks most promising. We're going to try some fine-tuning, and my hope is that we can squeeze out even better performance from this random forest by fine-tuning its hyperparameters. Hyperparameters, if you remember, are the settings of the algorithm itself that we don't learn directly from the data, but rather set before the training process begins. So for a random forest, this includes things like the number of trees, which is also known as n estimators, max features, which is the number of features to consider when looking for the best split. We have max depth, which is the maximum depth each tree is allowed to grow, and then also criteria for splitting nodes like min sample split. One systematic way to find a good combination of hyperparameters is to use grid search. So Scikit-Learn's grid search CV from the Scikit-Learn model selection module exhaustively tries out all possible combinations from a grid of hyperparameter values that you specify, and it uses cross-validation to evaluate each combination. So we define param grid RF. This is a list of dictionaries where each dictionary defines a set of hyperparameters to try. So in our example, we have one dictionary. You'll notice the naming syntax for specifying parameters in our pipeline. You essentially have step name, double underscore, and then parameter name. So forest CLF n estimators refers to the n estimators hyperparameter of the random forest classifier step, which we named forest CLF in our pipeline. And we're telling it to try n estimators of 50, 100, and 150. We're telling it max feature options of square root, log 2, or none. We also define max depth options of none, 10, and 20, and min sample split of 2, 5, and 10. We then again set up our forest pipeline. So this is the same one that we set up in the previous cell here. We're just repeating it for clarity. But what we then do is we create a grid search CV object. So the first argument in this is the estimator to tune. In our case, it's our forest pipeline for grid, which includes the scalar and the based random forest classifier, as you can see here. The second argument is our param grid RF. CV equals to 5 means it will perform 5-fold cross-validation for each and every combination of parameters in our grid. Scoring ROC AUC is our evaluation metric, and return train score true is useful because it allows us to see training scores for each parameter set, which can help diagnose if a particular set is overfitting badly even during the search. Verbose 1 will print messages as it works through the combinations, and njobs is -1 tells grid search CV to use all available CPU cores on your machine, which can significantly speed up the search process since many model trainings are happening. So I'm going to go ahead and run this, and then we'll talk through the rest of the code, as this can take a while to run, because if you can see, we've essentially got fivefold cross-validation on 81 different combinations of our hyperparameters here. So that's a total of 405 different combinations, and so this might take a couple minutes to run. So talking through the rest of this command actually runs the entire search process, and after fit completes, grid search CV stores the results. There are a few different attributes we can access. One is best params, which gives us a dictionary containing the combination of hyperparameter values that resulted in the best cross-validation score. Then we have the best score attribute, which gives us a best mean cross-validated ROC AUC score. And then we also have the best estimator attribute. So this is very important. This is the actual pipeline object already refitted on the entire X train and Y train using the best found parameters. And we're storing this in a variable called the best RF model GS, short for best random forest model grid search. So as you can see, this is now run. And if we look at the output, we can see it's identified the parameters that gave the highest average ROC AUC during the cross-validation runs. So a max depth of none, max features log 2, min sample split of 2, and number of estimators 50. And it also tells us what the best score was. It's 0.9924. And if we look at the default random forest score that we got previously, we would see that it's 0.9884. So we've made a significant improvement on the default. Now it's worth mentioning that grid search CV is thorough because it tries every combination. However, if your hyperparameter space is very large, so you have many parameters or many values for each, grid search CV can become computationally prohibitive. So an excellent alternative to that is randomized search CV. So this is also found in the Scikit-Learn model selection module. And instead of trying all combinations, randomized search CV samples a fixed number of hyperparameter combinations controlled by its n iter argument. It does this from probability distributions that you specify for each parameter, as we've done here. So this could be a uniform range for continuous parameters or a list of discrete values. This approach is often much more efficient than an exhaustive grid search, especially when some hyperparameters have a bigger impact than others. So the setup is similar, but instead of a fixed grid, you provide distributions for each parameter. Now for this tutorial, we'll just proceed with our result from the grid search cell above, but randomized search CV is a very valuable tool to keep in mind for more complex tuning tasks. So now that we have our best fine-tuned model, which is our best RF model GS variable, it's insightful to look at what it has learned. So for tree-based ensemble models like the random forest, we can examine feature importances. This tells us which input features the model considered most influential or important when making its predictions. So let's walk through this cell. We start with our best pipeline. Then to get the actual random forest classifier object within this pipeline, we use final model pipeline, name steps, and then we specify forest CLF, which is the name we gave to the random forest step. So just to recap that, here's our pipeline, and forest CLF is our random forest classifier within this pipeline. So this classifier object actually has an attribute called feature importances, which is a numpy array containing an importance score for each feature, and these scores typically sum to 1. We then get our original feature names, which are the columns of X-train, as our scalar step doesn't change their order, and we create a pandas series mapping these scores to their feature names, which makes it easy to sort and plot. The print statement here shows the top 10 most important features and their scores, and we use some matplotlib code to generate horizontal bar charts to visualize the top 15 features. So I'm going to go ahead and run this, and looking at this output, you can clearly see which features the fine-tuned random forest model relied on most heavily to make its classifications. So for this breast cancer dataset, features like worst radius, worst concave points, and mean perimeter often appear at the top. This kind of information is not only useful for understanding your model, but can also provide valuable biological insights, potentially guiding further research or suggesting a smaller subset of features that could be used to build a simpler, more interpretable model if needed, without too much loss in performance. So now we arrive at the moment of truth. We're going to take our final best fine-tuned model pipeline, which is the final model pipeline object, and we're going to evaluate its performance on the test set. So that's the X test and Y test variables. And if you remember, this is the data that's been completely locked away and untouched throughout our entire development, exploration, and tuning process. So the performance on this test set gives us our most unbiased estimate of how well our model is likely to perform on new and unseen data in the real world, assuming that the new data comes from the same distribution as our original dataset. So let's walk through this. First, this line uses our best pipeline to predict the class labels 0 or 1 for the test set features. And remember, when we call predict on the pipeline, xtest automatically goes through the scalar step. So it uses parameters learned from xtrain before the random forest classifier makes its prediction. Next, with this line, we get the predicted probabilities for the positive class. So that's the malignant class or class 1. And we need these probabilities for calculating the ROC area under the curve, which is our evaluation metric. So we then calculate the test accuracy and the test area under curve with these, and we're going to print them here. So if I run this and we look at the top 3 lines here, we see a test accuracy 0.9737 and a test area under curve of 0.9962. Now the confusion matrix from Scikit-Learn is also very important. So we can compute this using the true test labels, y-test, and our predicted labels, which is y-test pred, which we created up here. And from this we can create a confusion matrix, which essentially tells us the number of true negatives, false positives, false negatives, and true positives. So we use the confusion matrix display to plot this matrix nicely. And that's what we see here. We'll talk through this in a second, but let's just finish the code. So this part calculates and plots the ROC curve for the test set. So this ROC curve function from Scikit-Learn metrics essentially returns false positive rate, true positive rate, and thresholds. And if we go ahead and just look at the output, we see the following. So let's just talk through these images quickly. So this is our confusion matrix. We can see the number of true negatives we predicted as correctly, the number of true positives we predicted correctly. We had no false positives, which is good, but we did have 3 false negatives. So that means we predicted these 3 as benign when they were in fact malignant. Now, if we go down to the ROC curve, the diagonal line here represents a random chance model. So a good model's curve will bow out towards the top left-hand corner. And the area under this curve, this orange line, is our test area under curve, also shown in the legend here in the bottom right. So the performance metrics that you see here, especially the test area under the curve and a careful look at the false negatives and false positives in the confusion matrix, are your best estimates of how well this specific model trained with these specific hyperparameters would perform if it were deployed on new unseen patient data, assuming that the data is similar to what we trained on. Now, it's crucial that you resist any temptation to go back and tweak your model further based on these test set results, because if you do that, you're effectively using your test set as part of your development or tuning process, and it will no longer be an unbiased estimator of true generalization performance. So this test set is only for one final and honest look. Now, if this were a real application that, say, was now approved for use in a clinical setting or as a research tool, there are a few more critical steps beyond just this notebook. So in this final cell, we'll briefly talk about how you would save your trained model pipeline and next steps. So here we use the joblib library, which is generally efficient for saving and loading Python objects, especially those containing large NumPy arrays like we find in Scikit-Learn's models and pipelines. So we specify a file name, and joblib dump saves our entire final model pipeline, which includes the fitted scalar and the fitted random forest with its bet type of parameters. It saves those to that specified file. And this PKL file can then be transferred to another environment or application, and there you could load it back in and you could use it to make predictions on new unseen data without needing to go through the whole training process again. Now, beyond just saving the model, a real-world deployment also involves other things, so deploying, monitoring, and maintenance. So deploying could mean integrating it into existing hospital software, creating a web service API that other applications can query, or deploying it on a cloud platform. For monitoring, it's vital that you keep monitoring the model's performance on new incoming data. So you track its accuracy, area under curve, and especially critical error rates over time. And you're monitoring for things like data drift, which looks at if the characteristics of the new patient data is significantly changing from what the model was trained on. And there's also this idea of concept drift, where you're looking to see if the underlying relationship between the cell features and the diagnosis itself is changing over time, perhaps due to new subtypes of cancer or a change in diagnostic criteria. Now, for a medical model, setting up alerts for any significant drop in performance or increase in critical errors like false negatives would be essential. And when it comes to maintaining, machine learning models are not usually set and forget. So you'll often need to regularly retrain your model on fresh, up-to-date data to ensure that it remains accurate and relevant over time. So this also involves version control for your models, the code used to train them, and also the datasets themselves. So that completes our comprehensive walkthrough of an end-to-end machine learning project using the Wisconsin breast cancer dataset as our example. We've journeyed all the way from loading and understanding the data through extensive exploration and meticulous pre-processing to selecting, training, and fine-tuning our models, and then finally performing robust evaluation on our held-out test set. The key takeaway, I hope, is the importance of a systematic step-by-step process. Now, while the specific algorithms and techniques might change from project to project, this overall framework provides a solid foundation for tackling machine learning problems in bioinformatics informatics and beyond. So I hope this has been a helpful and clear guide for your own future projects. But that's all for this video. I'll see you in the next one, where we're going to further deep dive into classification, and we're also going to look at extracting features from images of cells using Cell Profiler, and also go a bit more in depth on deploying our model in a pipeline beyond just the Jupyter Notebook itself. So I'll see you in the next video.